Hi. In topic 2, when we discussed the simple architecture, we introduced several instructions in the form of opcodes together with a memory reference. I just want to review that and consider what appears to be a weakness in the instruction set that we considered. So, just to remind you, um, just remind you, uh, we looked at instructions of the form store memory address, add memory address, subtract or sub memory address, and halt, just to give you a random sample of the small number of instructions that we looked at. Well, um, each instruction in the form store memory address is going to be represented in binary, as a binary sequence, in the sense that we're going to allocate a small number of bytes to represent the opcode, or the short form of the instruction name, and followed by a particular memory address. So again, I haven't any particular uh, memory size in mind, but typically we'll use a binary number to form a memory address, a main memory address from that. So just to look at these instructions very briefly, store memory address simply means store the value of the accumulator, the value in the accumulator at this particular memory address. Secondly, add memory address means add a number to be found or to be fetched from this particular memory address with or to add it to the number found in the accumulator. And thirdly, leave the result in the accumulator. And a subtract instruction, whose short form is sub, very similar to the add memory address instruction. So let's just consider uh, um, the following diagram very briefly. This represents the main memory shaded in blue, and I've got an address register AR and a data register DR, and we use this diagram to explain uh, the memory cycle, the instruction execution cycle, namely fetch an instruction, decode it, and then execute the instruction in the following way. The program counter is actually going to contain the next instruction, the address of the next instruction to be executed, and to fetch that next instruction, the relevant memory address is going to be placed in the address register. The main memory is going to be instructed to perform a read operation, and what comes out is the opcode plus next memory address, or the address memory associated with the instruction. So uh, the uh, and so on and so on. I'm not going to explain this because it's not actually relevant to what I want to do at the moment. But most of you who are new to the subject need to come to understand uh, the constituents and the operation of this system here. So it's to fetch an instruction and decode it. In other words, you're going to send an opcode to the instruction register, and this control unit is ready to dispatch various signals which will enable the instruction to be realized. For example, if it's an add instruction, it's going to make sure that the number to be added, which is found in main memory, is going to be directed towards the ALU, and that number is going to be added to the number which is already in the accumulator, and the result placed in the accumulator. Well, to commission all that, the controller will actually issue one or more signals, hardware signals, which are going to control the various operation of things, including sending an add instruction, an add hardware instruction to the ALU. So I'm not pretending to give an exhaustive account at all, although that has been done elsewhere. So let's remind ourselves of the opcodes that we introduced last term. And I've given their representation as a decimal number. And of course, at the level of computer hardware, these decimal numbers will be given their binary equivalent. So, for example, 000 might be the binary representation of the instruction halt the computer, and the instruction in binary 010 simply means store the contents of the accumulator in the specified memory location, and 100 simply means load the data to be found at the specified memory location into the accumulator. Opcode 6, that's 110, means add data found at a particular memory location to the value found in the accumulator and leave the result in the accumulator. And similarly for opcode decimal 7. So you need 3 bits to represent 8 codes, obviously, but I'm going to introduce another opcode, which is JNZ, and I'm going to represent it by decimal 9. So JNZ is simply an abbreviation of jump if the value of the accumulator is not 0. Alright, jump to the label, jump to a specified location, and execute the instruction found there if the value in the accumulator is not 0. And I've also going to add another opcode, DEC, which means decrement, and it means decrement the number held or found in the accumulator by 1. And perhaps I can give it the decimal number 8 to represent the decrement operation. So what I want to spend a little bit of time explaining is this. What I'm actually showing here is a program, because in this column, in bold black, I've actually got a sequence of instructions formed by an opcode, like the opcode for load, which is 4, and an address, and here I'm using the address 1001. So what I want to do using this instruction is to load data found at this memory location 1001. In other words, which I've abbreviated by load A8. A8 is this address here, and it contains a number M, and so on. Now, what I'm trying to do here is to remedy an apparent deficiency in the small range of opcodes that our instruction set has, in the sense that I haven't mentioned, nor will I mention, an opcode for multiplication. I haven't got one. So the challenge I'm faced with is, can I get a short computer program at low level to perform a multiplication for me? And I think tentatively the answer is yes. And I can do that with the addition of these 2 opcodes, dec and jump not 0. So here's the dec operation, here's jump not 0. And notice that L1 is what I call a label, and it's actually naming this memory location 0000. So if this instruction is executed, what's going to happen if the value of the accumulator isn't 0 is to literally jump to this memory location which contains this instruction, and I shall execute this instruction again, and I might do that several times. So what I'm going to do is to, with just one more comment to make, what I'm going to do is to step through this quite short, 6, 7, 8 line program in order to understand how it's capable of multiplying any number m by any number n. And notice that I've got n stored in address location A11, so it's 1100, and I've got the number m, which I want to start with, stored at memory location, which I abbreviate by A9. It's 1011. So let's just go through this, and I note here I've got two little rectangular boxes which contain a correction. A8 here should read A9, and this address 1010 should read 1011. So let's run the program in our minds, as it were. So what I want to do is to load the data found at A8 into the accumulator. Well, what is that data? Where is A8? Let's have a look. A8 is here. Alright, this is location 1001, and the actual instruction is going to be 1001001, because the 100 represents 4, and that's the opcode for load. So let's find out. So we're looking at location A8, and it contains the number m. So the computer's being instructed to load the integer m into the accumulator. This is what load A8 does. Let's have a look at instruction number 2. It says add the number found at address A9 to the number in the accumulator, perform the addition and leave the result in the accumulator. So let's see what's in A9. What is in A9? Gosh, it's another m. So what we're going to do as a result of this addition is to add m to the value already in the accumulator, which, if you'll remember, is m. So I'm adding m to m and leaving the result to m in the accumulator. And okay, so let's have a look at the third instruction. It says store the value found in the accumulator, which you'll remember is 2m, at this location. Well, it's A9, because I've corrected it. A9. What's in A9? A9 used to contain m, and I'm going to write 2 times n, 2m, in this memory location. Instead of m, I'm going to write 2m. So I'm overwriting this integer by 2m. And then the fourth instruction is load the contents of A11. Well, what does A11 contain? What does address 11 contain? This is address 11, and it contains the number n. So this instruction says load the value found in location A11 into the accumulator. So I put n in. The next instruction says decrement the value of whatever's in the accumulator by 1. So I'm going to perform that operation, which means subtract 1 from n. So I'm left with n minus 1 in the accumulator. And then the sixth instruction is store whatever is in the accumulator at memory location A11. Well, let's do that. A11 actually currently contains n, and I'm replacing n by the contents of the accumulator, which, if you remember, is n decremented, n minus 1. So I'm going to replace n by n minus 1. And then I'm going to execute this instruction. Jump if the value in the accumulator is not 0. And I'm assuming it's not 0 because I'm also assuming that n is, say, a positive integer, maybe 10. Let's supposing it's 10. And the accumulator at the moment contains the number of 9. Memory location A11 contains the number of 9, which was the original n take away 1. So it's the value of the accumulator isn't 0. So what I'm going to do is to jump to this instruction and execute it all over again. I'm jumping to this labeled statement. This is a label which labels this instruction. Or better still, it labels this binary sequence, which is an opcode together with a memory location. So what it says is load the contents of A8, which, if you remember, contains the number m. Add the number that is found in A9. Well, do you remember what A9 currently contains? It's twice m, 2m. And add the two numbers together, so I'm adding m to 2m to get 3m. And then I store the result, i.e. 3m, in location A8. Well, A8, I'm going to... sorry, it should be A9, shouldn't it? Store the value of the accumulator. Store 3 times m into location A9. You remember this was 2m, but I'm now overwriting it to become 3m. And I'm loading the value in the accumulator. Loading into accumulator the value of A11. Well, A11, I hope you remember, contains the number 9, which was n minus 1. Load that into the accumulator, decrement it by 1, and you get 8. And store the value of the accumulator, that is 8, into location A11, which is this. So this now contains the number 8. This contains 3m. This still contains the integer m. And what I'm going to do is to jump to label L1 if the contents of the accumulator is not 0. Well, it's not 0. I just told you it's, I think it's 8 now. I don't think I've tripped up there. It contains the number 8. So once again, I execute the sequence of instructions all over again. Load the contents of A8, which is m, into the accumulator. Add the contents of location A9, which now contains 3m. Store the result in the accumulator, so I've now got 4m. Store the value 4m in location A9, so I'm overwriting the 3m I had here by 4m, 4 times m. And then I load the contents of this location into the accumulator, which I think was 8. And I'm going to subtract 1 from it to give me 7, then load the value 7 from the accumulator into memory location A11, which is here. So this is now going to contain, is it 7? I can't remember. 7. Well, I think you can see how it goes. I'm going to execute this sequence of instructions for as many times as the value that was originally in this location. N was here. Once around the sequence of instruction, it's going to be decreased by 1, then 2, 3, 4, 5, 6, 7. And eventually, the value of that results from decrementing the number found in location A11 is going to be 0, in which case I don't jump back to L1. I'm going to halt the computer. It's done its job. What we've accomplished is to obtain the result of multiplying m by n. And that value, m multiplied by m, is going to be contained in this memory location, A9. And, and as you can see, we've got to the stage of multiplying m by n by repeatedly adding m to itself n times. We've executed this sequence, I think, n times, in which case the value in A9 is m times n. M times n, the result of adding m to itself n times. So hopefully you agree with what I've done here. Hopefully you can follow my ideas of, first of all, just to summarise, this is a location. This green column here are address locations written in binary. What this memory location contains is this instruction when expressed in pure binary terms. I've got a binary number represented by decimal 41001 and so on. And the more easy to read version of this and that and this and that instruction is given by load A8, add A9, but A8 simply an abbreviation for what is in fact is a 4-bit memory address. So hopefully you agree with my analysis of this very short program, and the important thing to notice is that I've created a way of multiplying two numbers given my very, very basic, simple instruction set. Okay, so thanks very much for your kind attention.